Welcome to Genetics 5, Hardy-Weinberg Equation. Hardy was a mathematician in England. Weinberg was a mathematician in Germany. They came up with this equation pretty much at the same time, about 120 years ago. And we've been using this equation ever since for determining gene frequency for a trait that exhibits complete dominance. So the Hardy-Weinberg equation makes a couple of assumptions. The assumption is that, one assumption is that we have two alleles at the loci. One allele is completely dominant over the other. For the Hardy-Weinberg equation to work, it's best to have a relatively large population, 100 animals or more. If you only have 10 animals, this might not work. Also, for Hardy-Weinberg work best, there should be little or no selection within your population. For example, if you're selecting against one particular allele in the population, it could distort the frequencies. We have to make some assumptions here, and one assumption is that P is a placeholder. It's the frequency of the dominant gene. So this is kind of a placeholder in our equation. The other assumption is that Q is the frequency of the recessive allele in our population. And the assumption is that we just have two alleles, so the two have to equal 100%. So here's that Hardy-Weinberg equation. So we've got three possible genotypes: homozygous dominant, your heterozygous individual. We also call this heterozygous individual as the carriers in our population, because phenotypically they show the same phenotype as the homozygous dominant, but they're carriers for that recessive gene. And then we have the ones that are homozygous recessive. Now, the frequency of homozygous dominant is going to be P squared. Frequency of carriers in our population is 2PQ. And frequency of homozygous recessives is Q squared. And of course, all these frequencies, there's just the three genotypes. They have to equal to 1 for 100%. So where does this equation come from? We can show that with this little illustration. So one thing for the Hardy-Weinberg equation to work, the males and your females in the population have to have the same alleic or genotypic frequency. So P squared is the frequency of the dominant gene in both the males and the females, all right? So we fill in the Punnett square with our ends, with our genes there. And then what's the probability of getting two dominant ends here? It's just P times P equals P squared. And then this particular square, the frequency of this square is going to be P times Q, or Q squared. Frequency of this square here is going to be P times Q, or Q squared. So we've got two squares that have a frequency of PQ. That's the frequency of our carriers. So 2PQ is the frequency of carriers. And then the frequency of the homozygous recessive is just Q times Q, Q squared. So that's the beauty of how this Hardy-Weinberg equation came about. All right, now we're going to put that equation to work. So suppose that 1% of the animals in our population are born with a genetic defect. So this genetic defect is recessive in nature, takes 2 copies of the gene for it to show up. The rest are either homozygous dominant or big N, little n. And phenotypically, we cannot tell the difference between these 2 genotypes. They're both normal animals, indistinguishable. All right. So we've got 2 categories of animals. We got those that show the genetic defect and those that are normal. All right. So we want to know what's the frequency of the recessive gene. We know that 1% of the animals have 2 copies of that recessive gene, but we might want to know what what's the overall frequency of that gene in our population. And of course, we said that was Q, frequency of that recessive gene. And what's the frequency of carriers in the population? So we want to know what percent of the animals are heterozygous. And we know that as far as the frequency of that, it equals 2 times P times Q. So we got to find out what Q is and find out what P is, and then we'll be able to solve for frequency of carriers. So here we have it all laid out. We want to find out what, we know what Q squared is. That's 1%. We want to calculate Q, or the frequency of that recessive gene. We want to find the percent carriers in our population. So here's the Hardy-Weinberg equation again. Frequency of homozygous recessive is Q squared. We know that's 1%. Change that to a decimal notation here. And then we should just be able to take the square root of this 0.01 to equal to Q. So here it is, Q is equal to the square root of Q squared, which is the square root of 0.01, which is 0.1 or 10%. That's the frequency of that recessive gene in our population. Now, since P plus Q equals 1, we know that P is going to be equal to 1 minus Q. So what's P equal to? P is equal to 1 minus the frequency, or Q. So 1 minus 0.1 is 0.9. So P is 0.9, that's the frequency of our dominant gene. Q equals 0.1, the frequency of the recessive gene. So the frequency of carriers then is going to be 2 times P times Q, or 2 times 0.9 times 0.1 equals 0.18, or 18%. So we'll go through another example now. Suppose that we've got Angus cattle. 9 out of 10,000 calves are red, the rest are black. So here we have our genotypes up here again. The black is dominant over the red, so these animals are black and these animals are red. You need 2 copies of that red gene. Only 9 out of 10,000 calves have those 2 copies. So we want to know the frequency of the red gene, that's going to be Q. We want to know what's the frequency of the animals that are carriers, so we want to know what percent of the animals in our population are heterozygous. So this is what we know. We know that 9 out of 10,000 calves are red. So we got to change that to decimal notation. So 9 divided by 10,000 is 0.0009, and that's Q squared. Frequency of the red gene is going to be Q. Frequency of carriers is 2PQ. So the frequency of that red allele in our population is Q. It's the square root of 0.0009. or 0.03 or 3%. 3% frequency of that red allele in our population. So we know that the frequency of the red allele is 3%. We know that P equals 1 minus Q. So we know that the frequency of our black allele then is 97%. What's the frequency of carriers in our population? 2PQ. Do the math here. And frequency of carriers is 0.0582, or almost 6% of our animals are carriers for that red gene, even though they appear to be black in color. In case you need more practice, and practice is always good, what is the frequency of heterozygous animals if 16% of the population shows the recessive genotype 2a's? Well, here's the answer to that question. Q squared is 16% or 0.16. The square root of 0.16 equals 0.4 or 40% is the frequency of that recessive gene. And frequency of the dominant gene is 0.6 or 6%. Frequency of carriers, 2PQ, is 0.48, or almost half the animals in this particular situation are going to be carriers. Not quite sure on the frequencies, genotypic frequencies that we have here. And that's the end to the genetics video on the Hardy-Weinberg equation. Have a good day.